Right, okay, this is chemistry paper 1 and this is part 4 of a series of 4 videos to explain chemistry for paper 1. Again, this is for everybody, whether you're doing foundation or higher, and if there's any parts that are just higher only, I'll mention them as we go along. So this last topic is called chemical and energy changes, and you'll notice that around the centre here I've got the pH scale because we're looking at chemical changes, so acid, neutral, alkali, and then I thought just for a bit of fun I'd just put some J's there to show joules for the energy changes. Right, so let's have a look at this topic then in order. So first of all, reactivity of metals. If we look at metals, generally when they react, if they are gaining oxygen, we say they've been oxidated, okay? Or if they're losing oxygen, they've been reduced. Now you've got to be a little bit careful here because oxidation is loss of electrons, and we've got that over here, and reduction is gain of electrons. Whereas oxidation actually means that it's gained oxygen. So be a little bit careful if they ask you to describe, especially with electrolysis. Oxidation is loss of electrons, but it's the gain of oxygen. Whereas reduction is the loss of oxygen, but it's the gain of electrons. If we just put any metal into here and combined it with oxygen, we would make a metal oxide. And I think that's quite straightforward. The one that's a little bit more tricky to think about is this, the displacement reactions. The more reactive a metal is, the more it will take over. They're like big bullies. If it's more reactive, it will bully and push the other metal out of the way. So for instance, if I had a reaction where I took magnesium and copper sulfate and I put them together into a beaker, magnesium is a bigger bully than copper because it's more reactive. So it will push copper off the sulfate and it will take its place. And I'd end up with copper all on its own and magnesium sulfate. So I've got magnesium as a solid, copper sulfate as an aqueous solution. The copper then is left as a solid and the magnesium sulfate becomes an aqueous solution. Now again, like I say, always think about which chemicals are more reactive. And that brings me over to this reactivity series. And literally, if you can learn this, then this will really help you to think about what's going on in different reactions. The reactivity series is the most reactive metals at the top, and they go all the way down to the least reactive metals at the bottom. Now you will notice in here you've got two non-metals. So you've got carbon at this point and you've got hydrogen at this point. And that helps us to put this reactivity series into order and also to tell us some of the different properties. So everything above carbon, so potassium, sodium, lithium, calcium, magnesium, aluminium, if I want to get those metals, I can't just go down to a mine and just say, oh right, okay, can I have a lump of potassium? Thank you very much. I have to actually extract it from the rocks that it's in, and they're called ores. So in order to react to these green ones at the top, I need to use electrolysis, and I'll talk about electrolysis in a minute. If I want to extract these metals from rocks, then I heat them with carbon. So zinc, iron, tin and lead need to be heated with carbon, and that helps to extract them from the rocks. These ones at the bottom here, they basically exist as lumps of metals on their own. Copper, silver, gold, platinum, and you usually see people like using these big sieves to take them out. So the reactivity series is really important, especially when we just talked as well about the displacement reaction, because if there's something that's further up the reactivity series, it will push away something that's lower down. So if I had lead nitrate and I put in calcium, calcium would push the lead out the way and it become calcium nitrate plus lead. And you could do that, you could make up equations for that. The next thing you need to make sure you know is the pH scale, okay? The pH scale is when we use an indicator, a universal indicator, or even litmus paper, and we put that into the solution. Now for this one, we're using universal indicator. And what happens is, if it is neutral, that means it's green, okay? Whereas if it's acid, if it's slightly acid, the solution will go yellow, more acid, orange, and really, really acid, it will go red. And really all that means is it's got more hydrogen ions. So these here have got a couple of hydrogen ions, then a few more, and then loads at this end. Whereas at this end, the alkali, so you start off with light blue, and these are the hydroxides, so your OH negative. So these are a little bit alkali, these are a lot alkali, and when you get up to number 14, it just means there's lots and lots of OHs. Now I think the really clever thing here is, if I put pH 14 alkali with a pH 1 acid, the number of hydrogen ions in the number 1 with the number 14 balances out, so I get hydrogens and OHs, put them together, I make H2O, and that's water. But I'm also left with the metal, so that's where I end up making my salts. And that's what the reactions are about when we're looking at making salts, okay? It's about making water, but then seeing what's left over to make the salt crystals. Now, there is a required practical, and this has come up as a practical in the exams, but they could use, and this is where you've got to be really careful, because you may learn about copper sulfate crystals and think, oh yeah, I know all about that. You get into the exam and then they start using zinc sulfate crystals, for instance, and you might say, oh, I don't understand, I don't know that one, I didn't learn that. The process is the same, they've just changed the chemical. So if I wanted to make a soluble salt from an insoluble oxide or carbonate, I take some acid. Now usually, if they ask you for a method, you should put quantities in. I usually say anything between 20 and 50 centimetres cubed is a decent quantity. So add 20 centimetres cubed of warm acid and then add some metal oxide. First of all, be very careful when you're heating up the acids, because they can produce dangerous gases. And when you add the oxide, you make sure you do it a small amount at a time, because otherwise it can bubble over. And you keep stirring until the solution is completely in excess. It means that all the particles have diluted into the solution and you've got some left over. And that's why you need to then filter it to get rid of the excess. And then lastly, you start evaporating your solution and you are left with crystals that you then leave to form. The slower they cool down, the bigger the crystals are. Now, there are certain rules for being able to name salts and working out equations. Now, if you learn these, you can literally put any acid into there, any metal into there, and you'll be able to work out this side. So the rule is, if I've got hydrochloric acid, it makes a chloride salt, sulfuric acid makes a sulfate salt, and nitric acid makes a nitrate salt. So if I took an acid and mixed it with a metal, I would make a salt and hydrogen. How do I test for hydrogen? It's a squeaky pop test. How do I test for oxygen? It relights a glowing splint. How do I test for carbon dioxide? It turns lime water cloudy. How do I test for chlorine? It turns damp litmus paper and it bleaches it. If I took an acid and mixed it with an oxide or a hydroxide, both of these make exactly the same thing, a salt and water. And then lastly, an acid plus a metal carbonate will make a salt and water again, but this time, because it's a carbonate, I also make carbon dioxide. Okay, now if we have a look over at electrolysis. Now, electrolysis is one of those that people really struggle with because they can't understand what's going on, okay? Now, if you get a question based on electrolysis, go for what you know, and that's the basics of electrolysis. What's it actually do? Well, what it does is you've got these electrodes here, and they are pushing electrons around into your solution. And normally with a circuit, it has to join in order for the electric to conduct around. But as long as these electrodes are in this solution and this solution conducts electricity, then it will still push the electrons around. Now, you've got your two electrodes that are called the anode and the cathode, and the anode is positive, A for anode, A for add, and the cathode is negative. In this solution, you've got these things called ions. So your negatively charged ions will go to your anode and your positively charged ions will go to your cathode. If you think about opposites attract. Now, the thing is with electrolysis, some people really struggle to remember which way around what goes on. And I made up this little story to help. Now, if you think about, if I had copper sulfate in this solution here, think about a copper, think about a policeman, a copper, and he goes to visit Annie the anode. Annie the anode is nasty. She's a horrible girl. So she actually strips the electrons off the copper. So now he's all naked. And he goes to visit Cassie the cathode. And she's nice. She's so nice, she gives him his electrons back so he can get he's covered over again. And because he loves her so much, he hugs onto her. And what that actually means is the anode is taken away, and we're back to this. Oxidation is loss of electrons. So the anode is carrying out oxidation. The cathode is carrying out reduction because it's gaining electrons. And the copper actually collects around the cathode, so you've got pure copper. Now, they could use any chemicals in there, and there are certain examples that are in your revision guide. And what you need to think about is they might use one of these in your exams, or they might alternate and change the metal. But generally, it's the same rule. Here, if I've got lead bromide, if I heat up the lead bromide until it's molten, at the anode, can you see the anode? Bromine, which is from group 7, will be oxidated and lose its electrons, so they separate out. Whereas at the cathode, the metal, the lead, will collect the electrons, and it will make lead, and it will hug on to Cathy the cathode again. So the metal is collecting at the cathode. If I look at this one, heat copper chloride until molten. The chlorine goes to the anode. So you can see, again, group 7 goes to the anode and releases some electrons. Oxidation is loss of electrons. Whereas the cathode, the metal goes there again, and it collects its electrons and makes a full copper. So here, 2 examples to show the metal goes to the cathode and the group 7 goes to the anode. There's another couple here. This one here, extraction of metals, and this links back to the reactivity series I just talked about. If it's more reactive than carbon, aluminium oxide will mix with cryolite. And if you see here, look, the gas is releasing electrons at the anode, and the metal, again, is collecting at the cathode. So a general rule of thumb here is, if there's a metal involved and you're not sure, the chances are that's going to be collecting at the cathode. The last one, and this is where you highlight here, and this is like the sort of back questions at the back of the paper, the really tough ones, is they might give you a question that says the electrolysis of an aqueous solution, and you've got to try and work out what's going on. And generally the rule is, if there's oxygen present, then that's what you'll make, unless there's a halide, unless there's a group 7. If there's a hydrogen produced, if metal is more reactive than hydrogen. If not, then sodium, so for instance, sodium chloride solution, the chloride will be made at the anode and the hydrogen will be made at the cathode. Right, the last 2 things we just need to look at is endothermic and exothermic reactions. Exothermic gives off heat to the surroundings, and that's because it's making bonds. Endothermic takes in energy from the heat to break the bonds, and there is a required practical that you need to use a polystyrene cup as it's a good insulator, so that you can actually work out the amount of energy being taken in or given away. If you're asked to draw the profiles, think about standing on a diving board, jumping off, landing in the swimming pool. That's exothermic reaction. And if you think about endothermic, open the front door, walk in the house, close the front door. Okay, and make sure you label the reactants, the products, and the activation energy there for exothermic is just from there to the top, and activation energy from there to there for the endothermic reaction. Okay, that's a lot to go through. If you want to stop the video at any stage and actually make a mind map, you can. But that's everything that you need for paper 1 for your chemistry revision.